Hey guys, we're going to review all of the various homework questions. Now, if you're thinking to yourself, Mr. Erico, I don't need to see all of the homework questions. I only need to see number 13. You know what? That's great. Skip to somewhere else in the video. Because what I'm going to do is I'm going to go through them in order. Okay? Now, what I thought I would present right at the beginning, though, is the following. A list of sort of the steps that you ought to follow for each of the various questions, right? So if you got stuck, right, it's entirely likely, for example, that number one, maybe you didn't, I don't know, draw a diagram. I've been telling you the whole year, right? Draw a diagram. Draw a diagram. Always draw a diagram. And if you don't, then you're probably going to get stuck. All right, the next thing that you got to do as you're trying to solve the problem is decide if it's an isolated or a non-isolated system, meaning do you start with delta E equals 0 or delta E equals work? If there aren't any non-conservative forces there, then you're going to go with delta E equals work. On the other hand, if it seems like it's only like gravity or springs, then you've got a situation where it's an isolated system, right? Only conservative forces act. All right. Next thing that you'd want to do is decide what types of energy exist at various positions. So you'll see me do that for each of the questions. Your options are pretty much just these three, right? If it's moving, there's kinetic energy. If it's higher than the lowest position, then there's gravitational potential energy. If there's a compressed spring, then there's elastic potential energy. All right, and then plug in and solve. All right, that's the part where there's algebra. And then lastly, if you do get stuck, like ever, go look through the notes packet. There's probably an example similar to the one that you have a question about. If you look through it, you may discover there's none exactly like it. That's normal. I'm not going to give you the exact same question in your notes that you're going to do in your homework, right? It's got to require a little bit of extra thinking on your part if you're going to learn something new from it. If you got stuck on this one, if I were you, I would actually go back and look at example 11 in the notes packet first, because actually example 11's got a lot to do with what's going on with this one. All right. Now, it's got a loop-the-loop in it, and it wants to know things like, okay, what's its speed at point A, and it tells you where it's released from. And there's some things that seem like they're maybe missing, like what is its mass? You might like to know for part A, but they tell you that later on in the question. All right, now, first let's decide, is it an isolated system or a non-isolated system? If it's an isolated system, then that usually means that the thing that's lacking is friction, and it says right there that it's going without friction. Okay, so we get to ignore friction. That means that we'll be able to say delta E equals 0. Fantastic. All right, next, we've got to decide what types of energy exist at the 2 points we're interested in our system. They tell us where it starts, right there, yes? Okay. And the spot they're asking about is at position A, which is here at the top of the track. All right, so the initial energy is just going to be gravitational potential energy, because it says it starts from rest up there. All right, when it gets to position A, it's going to have kinetic energy for sure. Whoops, that's a K. Believe me, please. All right, and it's also going to have some gravitational potential energy, depending on how you want to work out the problem. Probably for most of us, we're going to go something like saying, well, at the lowest position there, that's going to be a height of 0. It's not on the ground at position A, so that means that it has some gravitational potential energy because, as it turns out, it's a distance of 2r, whatever that is, off the ground. All right, now let's go ahead and plug in what we can. The initial energy, we said, is UG. Would probably have to call that UG initial. For the final energy, it's got kinetic energy and gravitational potential energy. We'll call that one UG final. Okay, the point is to get the speed at A. So that means that we'll put in 1/2 mv squared for K. For UG final, All right, the formula is mgh. We'll call that H final because it's not the same as H initial. So there we have mgh initial. All right, H initial. In the diagram it's labeled as H. In the prompt, though, they tell you that H is 3.5 r. That's 3.5 times the radius. So we'll go ahead and say H here is 3.5 r, which means the initial potential energy is 3.5 mgr. So notice I put my coefficient out front. All right, for the final gravitational potential energy, it's a distance of 2 times the radius off the ground. So that would be plus 2 mgr. And then, of course, kinetic energy is still 1/2 mv squared. All right, if at this point you're thinking, how can I get the answer? I don't know m. The m's conveniently cancel out. All right, so that leaves us with 1/2 v squared plus 2gr equals 3.5 gr. All right, we got to combine our like terms, right? We're trying to solve for v. So if I combine my like terms, I'll end up with 1/2 v squared equals 3.5 minus 2 is 1.5 gr on the other side. There's the decimal point there, I swear, right there. All right, let's multiply both sides by 2. So now we're going to have v squared equals 3 gr. That means that v equals the square root of 3gr. If you're thinking, I don't like that answer, that's not enough, it's a symbolic answer, and that's fine, right? Okay, now, part B wants to know what the normal force is at point A if the mass is 5 grams. So this is where you're going to go back to dynamics, and you're going to draw in your forces and such. I'm kind of running out of space and time here, so if you need further help with that, what you should do is draw a force diagram, look at example 11, and you should be able to figure out which direction to have normal force, gravity, and centrifugal force pointing. And then it's just a matter of plugging numbers in. All right, now you're given a mass, it's 5 grams, that's very small. You're not given a radius, however, you're going to discover that the radius actually cancels out. So just bear with me, plug into it, and you'll see that the radius cancels.